Okay, Georgia Tech, you may begin.
Good morning. We are the Georgia Tech Energy Club team, and we would like to go ahead and thank the competition organizers for allowing us this opportunity to learn about a holistic process for developing a distributed PV system, as well as the judges for their time today. So let's go ahead and look at our team real quick. So my name is Jake. I am a mechanical engineering major, and this is my fourth year participating in Solar Cup. I'll be covering the overall system goals and the battery system. Andrew and Joseph are second year Solar Cup participants and will use their industrial engineering knowledge to talk about the financial analysis and their electrical engineering background to talk about the distribution impacts. Hassa and Garrett are first-time participants who will be sharing the details of the conceptual design. So what are the system goals and the district goals for the Lake Nona Town Center? So first of all, the system should benefit the Lake Nona community through providing financial returns by lowering the cost of electricity. And it should also provide energy security in the case of outages. Second, the system should synergize with electric devices like EVs and technology like smart buildings to help decarbonize the grid. The design should be efficient and take into account the particular context of the district. Third, the system should exemplify Lake Nona's innovative mindset by successfully deploying emerging technologies. It should further the district goal of inter-business collaboration as well. So now I'll hand off the system description to Hassa.
So we have three main types of systems. We have our rooftop systems, which are our LNTC Building 2 in the left middle and LNTC Building 1 on the bottom right side. We have our garage systems, which is Garage G in the top left, Pixon Garage in the bottom left, and Wave Hotel Garage in the top right. These parking garage systems can also be integrated with EV chargers. And finally, we have our supplemental systems, which is our field array and the photovoltaic system on the next page. So we chose these locations for our designs because we wanted them to be energy efficient and have minimal shading loss, which is why we only included 2 rooftop solar arrays. And also we included the garage systems and the ground mount and photovoltaic system because Lake Nona wants to be seen as a city of innovation. So we wanted solar panels in easily accessible areas, which will be easily visible by the public. So going on to the photovoltaic system, one of the other reasons why we included a photovoltaic system by the New Hope Road pond is because photovoltaics are very energy efficient due to the cooling effect of the water. So the reasons going on to the solar panel design, the reasons we chose the solar panels that we did, which is the SunPower solar panels for all of our rooftop systems and parking garage and photovoltaics, and then the Helion system for the ground mount, is because we wanted very energy efficient solar panels, which also had a low price per watt. We chose the SunPower system for the rooftops, parking garages, and photovoltaic specifically because of their very high efficiency rate, which is especially important for the rooftop and parking garage systems because they're very small. And then we chose the Helion system for the ground mount because although it is slightly less efficient, it is also cheaper. And considering that the ground mount is our biggest system, we wanted to have a slightly cheaper price on that. And for the inverters, we chose the Fronius for all of our rooftop systems, and we choose the SunGrow one for the photovoltaic and ground mount systems, so we could have a centralized inverters as they are our larger systems.
So the storage system consists of 2 PowerSonic ES 1000-2000S batteries with 4.2 megawatt hours of energy and 2 megawatts of power. The system provides value by shifting consumption to off-peak hours and by reducing the peak demand to offset electricity costs. Additionally, the battery can power buildings in the event of a grid outage, which provides greater security to the community. The batteries are located next to the Wave Garage and field array for ease of interconnection with the grid. The garage also provides the batteries shading and protection from the elements.
For our financial performance, all systems achieved a competitive IRR of 8.75% and a positive customer savings, assuming a 10% discount rate. Using some key assumptions based primarily on the 2022 NREL benchmark report, we determine our system has a monthly lease price of $37,000 and a 20 years customer savings of $3,400,000, which is calculated assuming a 2.5% utility charge escalation. Since the savings are sensitive to this assumption, we also confirm significant positive savings at lower rates. Now we go into more detail about our process to develop our solution.
A big constraint for our system that we had to work around was interconnection. Since our expected system for this area will be 1,906 kilowatts, we're far below the maximum threshold of 4,200 kilowatts. Since there are many nodes nearby with this threshold, we have many options for interconnection and can adjust if necessary. However, an interconnection at the location our arrow points to would be close to our field array, which has the largest output. It is also closest to where this node branch connects to the rest of the system, meaning there's less chance of the threshold being lowered in the future due to the interconnection of other systems. For the photovoltaics, we had a lower threshold of 2,000 kilowatts, as well as limited interconnection points. We chose a location that is slightly further because of its location further up the branch, again, making it at less risk of decreased thresholds in the future. Additionally, through a combination and balance of our PV systems and 4.2 megawatt battery, we can ensure to always remain under the maximum threshold either way. Surge protectors and smart inverters will need to be installed for this photovoltaic system due to the lack of infrastructure near the system. Moreover, both systems can be islandable, since our system output combined with the battery storage would permit the building to operate like a microgrid for most days.
So in terms of the actual systems, one of the main questions is how can we best arrange the solar panels to get the maximum output? And so we could have a very flat system that's really close together, so that there would be a tilt loss but no shading loss, or conversely, we could have a fully tilted system that's really far apart or really close together, but there'd be a shading loss or just be super inefficient. So the ideal system would be a mix of trying to minimize both the tilt and shading losses. And so how do we do that? We did that experimentally in Aurora Solar on the side of the field array. We modeled what would be like a 2-story building, which is roughly the average height of our rooftop and carport systems. And then we put 2 rows of 5 solar panels on it, and then varied the spacing and the tilt angles of these, and then ran performance simulations, took that data into Excel, and then ran a couple analyses on it. And basically this chart is a sample of some of that data. So as you can see here, the optimal spacing for almost all the tilt angles was at 1 panel length in between each row. And so then if you're to zoom in on that point, you'd also see that 25 degrees had the maximum output. And so then we chose all of our systems to be at 25-degree tilt angle and 1 panel length spacing in between, and they're all facing due south as well. And then we also had one other consideration, and that was what if we had a mixed tilt system? And so we looked back at the data and determined that the optimal system here would be from 12 degrees from April to September, and then 40 degrees from October to March. And as you can see here on this chart, that involved about a 4% greater output than the 25-degree static tilt system. However, due to some greater upfront costs and maintenance costs, the marginal benefit was actually outweighed by the overall increased costs. And so the static tilt was more economical in the end. And so we ended up going with the 25-degree static tilt system.
So the sizing of the battery was done through an iterative approach. We started with the inputs of our PV production, which was modeled in Aurora Solar, as well as the electricity rates from the local utility. And these were input into the NREL tool Reopt. And using its base assumptions, it recommended a system size and created a system dispatch strategy. And that dispatch strategy was then input into Energy Toolbase to find the total offset utility costs or the savings of the system. Then that was put into our Excel model to find the 20-year customer savings. Then we adjusted that initial size of the system in Reopt and checked whether the savings would go up or down when we increased and decreased the size of the system until we converged on an optimal solution, which is shown right there. Then we also investigated how what the resiliency provided by the battery was. So there were 2 metrics of building consumption that we looked at: peak load and average load. For the peak load, which is like the maximum and the worst case for the battery system, we found the system actually had a 100% survival rate for outages of average length for 14.6 hours. When looking at the average load, which was a little bit more representative, then it could actually serve the load for 100 hours, which could be, through a hurricane or other significant weather event.
Regarding the construction of our project, here you can see our ground mount system in yellow, as well as the buildings we plan to install solar on. The red boxes show where the construction crews could set up in order to have a location to work out of when installing the solar. The staging area next to the ground mount system will have minimal impact on the local area during construction, with a side road for machinery to have easy access. For the other staging area, we chose an area that was on the bend, giving machinery multiple paths, and a location that was central to all of our system sites. As for the photovoltaic staging area, we chose an area close to the main road and on the side that is closest to the proposed photovoltaics location, making transportation of equipment and materials easy. Another thing to note is that since the lake is artificial, the erosion done by construction will be lesser than if the lake was natural. Here you can see our project construction timeline. Some important things to mention briefly are the total construction time that we estimated to be around 8 months, along with the interconnection and permitting time of 90 days, which is determined based on the Orlando Utility Commission's policy.
For our financial analysis, we set our target IRR at a market competitive rate of 8.75%, and we also wanted to achieve positive customer savings. We considered the existing blended rate, cost per watt for both rooftop and battery-tied systems, and the available financial incentives such as the federal ITC. We determined these considerations through the sources shown below. We then downloaded the PV production profiles from Aurora Solar for each system and ran them through Energy Toolbase to find the offset utility costs. We then used an Excel-based financial model to output the lease price and 20 years customer savings. The graph below shows the investor side profitability of our system over 20 years, and that our system has a payback period of 12 years.
All right, so to wrap up, let's talk again about the system goals and benefits. So the system directly benefits the district by generating over $3 million of savings over 20 years, as well as providing resilience to the office buildings in the cases of outages for very significant durations. The system also facilitates electrification by producing over 3,800 megawatt hours annually, which equates to 1,600 tons of CO2 offset. And it can also connect with smart buildings and EVs. The photovoltaic would also cement Lake Nona as being on the cutting edge of solar technology. And the project's collaborative nature would allow businesses to work together in investing in this project. So once again, thank you for listening to our presentation, and we'll open it up to questions now.